plus another Z. Yeah, so I times ZL plus C is definitely greater than IZL. So the voltage available to the relay, if you look from the fault point, the gradient, if you look at it, the voltage available to the relay is much higher than what the relay would have calculated as IZL. VZL is equivalent to the voltage that is developed inside the relay, multiplying the current with the impedance ZL. So V minus IZL is greater than V. So if IZL and V minus IZL and V, they are in, I should not say greater than, IZL is, and V, if you take two of these, calculate V minus IZL. V and V minus IZL are in the same direction, right? So if you look at this, the phase angle relationship between these two, they are in phase. So if we get that, then we decide that we don't want to trip. So if for an external fault here, we determined that V and V minus IZL are in phase. Now let's look at the internal fault of this. ZL2 is the impedance up to the fault point, which is definitely less than ZL. So I times ZL2 is what? What is this? This voltage is the voltage available to the relay V, but IZL, which is inside the relay, is greater than this value, right? So V minus IZL is on 180 degrees out of phase with the voltage V. So when you compare this phase relationship for any fault inside section A and B, we find that V minus IZL is 180 degrees out of phase with V, so we allow the relay to trip. In the first case, the previous case, V minus IZL and V were in phase, so we blocked the relay from tripping. And in the next case, V minus IZL and V are 180 degrees out of phase. We allow the relay to trip. Now we look at the external fault. The current that is flowing through the relay is reversed because it is fed from the remote end B towards the fault. So IZL is essentially in the opposite direction when compared to the voltage V, which is essentially the fault current multiplied by this impedance ZL3, right? So V and V minus IZL, V minus IZL vector will have a magnitude which is greater than V, and also it will be in the same direction. So even in this case, if the fault is behind the relay, we see that these two vectors are in phase. And now we also found that if the fault is outside the protected zone, outside the set reach, then the relay is also, these two voltages are in phase. But if the fault is in between A and B sections, then these two vectors are, quantity V and V minus IZL are 180 degrees out of phase. So the trip criteria is when they are out of phase, you trip it. When they are in phase, you block it. This is the basic concepts of all the distance relays that has been developed. So we use a phase comparator, and then V and V minus IZL is fed, and then we look for the angle. And suppose if I set an trip angle is alpha, and alpha is a phase angle between V minus IB is greater than 90 degrees. If it is greater than 90, we trip it. If it is less than 90, we block it. What does it do? It is nothing but, this is IZ drop here, and then this is the IZ drop. This is the voltage. I'm just assuming that some voltage has got arcing resistance. That is why it is like that. This is IZL, and then this is V minus IZL. When I set this angle to alpha, what does it mean? It is a locus of a point which moves such that the angle between these two vectors is always 90 degrees. What is this? This is just a geometry from the geometry. We know that this becomes the diameter of a circle. The angle subtended by a diameter of a circle at the circumference is always 90 wherever the fault voltage is. So this is how you develop a circular characteristics. You take two voltages, V minus IZ and V, and then you compare the phase relationship between the two, and then you set it. So if you set it to 90 degrees, then as the limit, then it produces a circle. Suppose if this angle is set to 135, then what it does is it produces this diameter becomes the chord of a circle. So it produces an elliptical characteristics like this. And if the angle is less than uh, uh, 60 degrees, it's set to 60 degrees, less than 90, the chord and moves onto the other side of the diameter, and then you produce a characteristic called tomato characteristics. These are the various ways these characteristics are developed with a phase angle comparator. The same concepts are used. The real, if you take the real product of cosine product or dot product of V minus IZ and V, if it is positive, then we know it is it's blocking. If it is negative, then we allow it to trip. If this is 90 degrees, then you get a circular characteristics. The same concepts are used in microprocessor-based relays, but the way they do it is a little bit different. Now, how do we develop other characteristics? Instead of V minus IZ and V, if I take IX drop, reactance drop, and then we take the V, and then we get a characteristics like this, whereas any point which is moving on a straight line will always have an angular relationship of 90 degrees with respect to IX. So this is how we develop the reactance characteristics. Now, if you want ohm line here like that, then you set this, one of the inputs will be IZ minus V, and IZ will give you this. So this is how all phase angle relationships were done in digital relays, earlier portion of static relays. And a lot of these concepts are used in the microprocessor-based relays too. Now let's look at the type of faults in a three-phase system. We already looked through this during fault analysis. We have three phase to ground faults, A phase, B phase, and C phase, called single line to ground faults. And we also have phase to phase faults, A to B, B to C, C to A, that doesn't involve ground. And then we have double line to ground fault, or also called phase to ground fault, AB to ground, BC to ground, and CA to ground. Okay, and then we have three-phase faults with and without ground. When a three-phase fault occurs, it is symmetrical. There is no current going to the ground. The common shorted point will always remain at voltage potential 0, right? And then we have another one called cross-country faults. What happens is, if there is a single line to ground fault at one location, this makes other two phase voltages get elevated, right? Depending on the effective groundingness or not, if the system is effectively grounded or not. So that is Z0 minus Z1. That value is the one which increases the voltage on unfaulted phases. When this voltage goes up, there might be a flashover at some other point on the line, and then it creates another ground fault. A single line to ground fault at one end on one phase, and another line to ground fault on another phase at a different location. These are called cross-country faults. Now, what is our objective? The goal is to measure the same impedance up to the fault point, irrespective of the type of the fault, whether it is a phase to ground fault or double line to ground fault or phase to phase fault or a three-phase fault. We need to measure exactly pinpoint the location of the fault to make a decision whether to trip or not to trip, right? So relays measure the positive sequence impedance of line up to the fault point. So that is our aim here. When we design the relay, we just want to make sure that it measures up to the positive sequence impedance up to the fault point. Phase and ground distance relays, what they do is, if you feed the voltage as V, and then I said that you have voltage and current that is fed into the relay to detect the fault. For A to ground faults, you need a wave phase voltage and IA current plus K0 times IN. We covered this K0. We were looking at the transmission line impedance, and then I said this is the ground return path, that is ZM, and then we brought it as K0 times I1, Z1, right? In the previous slides, it is there. So when we feed, if we take the ratio of V and to IA plus K0 times IN, the ground current, the neutral current that is fed to the relay, then it measures the impedance up to the fault point. You can go through the derivations and look at it, but that is not covered here. But this is all you want to know. If I want to have A to ground fault, I need the faulted phase voltage, that is VA, divided by the faulted current plus some portion of the neutral current that is fed into the relay to measure accurately the positive sequence up to the fault location. Similarly, if it is a B to ground fault, then I need VB, the faulted phase voltage, and IB, the faulted current, plus K0 times the neutral current. And similarly, C to ground, VC and IC plus K0IN. If we feed this, then if it is a phase to ground fault, the relay measures only the positive sequence up to the location of the fault. Similarly, if you look at phase-to-phase fault not involving ground, then I need the voltage across the faulted phases. A to B, I need VAB, and then the currents IA minus IB are taken. The difference in these two phase currents, IA minus IB. If I divide VAB by IA minus IB, the relay measures the positive sequence impedance up to the point location where phase-to-phase A to B fault occurred. Similarly, for B to C, we need another measurement, VBC by IB minus IC. And for C to A fault, we need VCA and IC minus IA. So essentially, I need 6 different elements for measurement techniques to determine faults up to the fault point accurately, irrespective of type of the fault. So yeah, 3-phase fault and double underground fault can be categorized as a phase-to-phase fault or a phase-to-ground fault. Then they can be detected by both. Generally, phase-to-phase elements are used to detect double underground fault and phase-to-3-phase faults. So essentially, it comes down to having 6 different measurement techniques, methods to get 6 different elements with different voltages and current inputs to detect all types of faults. Now, if I want to protect a line from A to B, and I am feeding A phase, 3-phase voltages and 3-phase current at the relay location to the relay, or that is the secondary sides of the instrument transformers are connected to the relay. And then if I set this to 100%, as you know, there is another line section here, and there'll be a breaker here too, right? There will be a breaker here. And if there is a fault here, I need that, if there is a fault here, I need the adjacent line section to operate first before we open this line, because our intent is to only isolate faulted sections, right? So if I look at it and if I set from A to B, then there are some errors. The measurement errors are there. Line impedance calculation errors also are there. They may not be 100% accurate. They are not 100% accurate. And you have CT errors. We found that C rating has got 10% error at if the current is 100 amperes, or 3% when the current is loaded up to the rating of the CT. And PT errors are there. We have 1% or 1.2% or 0.3 percent errors. And then design tolerances are there in the relay too. If you add all these things, if I set the relay to 100% of the line, this might operate for a fault just outside also, right? Somewhere here, if within 10% of the adjacent line, if the fault occurs, then I might lose this section EB too, right? So it is important for us not to set this relay to 100% of the line we are trying to protect. So that's why we reduce this reach to about 80 to 85% of the protected line section, and from ZA, from substation A to substation B. This is, and then if the measured impedance is around 80 or 85% is less than the set value, then we allow the relay to operate without any time delay. If the fault is in the last 15% of the line, then we have to have another element which says that I'm not sure whether the fault is on the line or very close on the adjacent line. We wait for some time, allowing the relays to operate at station B, and then if it doesn't operate after some time, we trip this and take this line out of service. So it provides, you need a backup protection to cover the last 15% of the line section. Okay, the one which is set to underreach the line, that is what it is set beyond less than 100%. It is called underreaching zone or zone 1. And then the second one, you use a relay which is set 25% beyond the bus B, and this is called overreaching zone. So zone 2 tripping is always time delayed to coordinate with remote and breaker and line relays. So when I look at the way we set it, if I have a line section A to B, B to C, C to A, the first zone 1 from A to B is set to 80 to 85% without any time delay for operation. Then the next 15% of the line and adjacent 20-25% of the line is set with zone 2 that has a time delay that will allow this relay of zone 1 relay to operate. And if there is a breaker failure relay here, and then it will allow that it has to coordinate with the breaker failure relay too. Let's assume that this operating time is 1 cycle. For example, relay operating time is 1 cycle, breaker is 2 cycles. So 1 plus 2 is 3 cycles is the total clearing time under normal conditions for zone 1. And now if the breaker has a breaker failure, that is, it is 2 cycle breaker, I said. So well, let's say it is set to 5 cycles as breaker failure time. After 5 cycles, after the relay gives a trip command, that means 6 cycles after the fault initiation, it opens this breaker. This might take 2 more. This will take 2 more cycles, 8 cycles, right? So if the first relay fails here, and we have to allow for a breaker failure to operate, total fault clearing time for any zone 1 fault in this section is about 8 cycles. So I have to have this zone 2 greater than that, allowing this relay from relay at section A to take care of faults in the adjacent line section by the relays located at station B. So I have then typically zone 2 is set to about 15 cycles, and then that has to coordinate essentially with relays in the adjacent line section. So I have zone 1, zone 2. Sometimes you have an overreaching zone 3, which is set to cover the complete line section of the adjacent line plus some portion of it. So this is if there is a total failure at station B, this relay is going to cover and give protection for all the faults beyond section B and beyond section C up to section C2. So any lines which are going out of this should have a backup protection if you have zone 3. So this is called a stepped distance cream. It looks like a step. Zone 1 is instantaneous. Zone 2 operation is about 15 cycles or so. Zone 3 can be set 30 or 60 cycles, whatever the philosophy is. Essentially, this has to wait for all the relays in section B and C, zone 1 and C, and then backup relays in B to operate and also accommodate breaker failures timings on that. So zone 1 is typically set to 80 to 85%. It is called underreaching zone. This is a conservative approach prevents relays from operating for faults beyond the line section. And zone 2 is the overreaching, which is set at least to 15 to 120% of the line. And then typical setting is 125 to 150 of the protected line. These are all, I'm just mentioned it typical because there might be many reasoning beyond going into this setting. And then that particular engineer who is setting up setting might have a good reason to say that I need zone 2 to be much higher than this, or to the minimum. They can set it to the minimum. Similarly, zone 3 also covers 120 to 150% of the adjacent line, the longest adjacent line from station B. So now, when we set these overreaching relays to cover, oh, there's a question here. Yeah, there was a question to ask how to prevent zone 3 from fault stripping due to overloading instead of fault. It's a good question. We saw that we had load encroachment, right? Let's. Okay, let's go here and then see. See, this is the load region, right? So when I have section AB, zone 1 is set up to cover up to this, right? Yeah, it is assumed that is a circle. And then zone 2 is way beyond this, and zone 3 can come like this. So you have to make sure that your zone 3 is not getting into the load region. So modern relays allow you to go back and chop off the load portion and then they take care of this kind of problems. They can shape the characteristics to take care of that, whatever that load that we don't want it. So anyway, if the load comes into the tripping characteristics, it will be seen as what? It will be seen as a three-phase fault. The relay will trip. So that is why we know that the load region is the 37 plus minus 0.9 power factor. When you look at that, you try to cut off the portion. 0.85 is used sometimes, and then they try to chop the circular characteristics or whatever characteristics, so that if the phase relationship between voltage and current is less than 37 degrees, then you say it is a load, it's not a fault, and it has to be a three-phase condition. Now let's look at it here. I have a line section from A to B, and I have two transmission lines going from B to C and B to D. B to D is a longer line in this figure. Now a fault occurs on line section BC, and then the impedance of the line up to the fault point from bus from B is ZF. Now, the impedance seen by the relay at A is ZAF, right? It is going A to B impedance plus ZF. The voltage at the relay is what? When you calculate this, it is IA plus ID current, total current up to the fault point times ZF plus IA current times ZAB. So if you look at this here, it is, so ZAF is V divided by IA. I'm doing this, so it is ZAB plus 1 plus ID by IA times ZF. So what I see here is ZA plus ZF plus an additional quantity, which is depending on the ratio of the currents that is fed into the fault, D to A, times the impedance, actual impedance. So if there is no D current, then what is this? This is the actual impedance from A, substation A up to the fault point, that is ZAF, right? Now with this current that is feeding in from the adjacent line section for the to this fault, you have an impedance that is added on. The relay thinks that there is an additional impedance, which is the ratio of ID by IA times ZF. This is called the apparent impedance seen by this. And this phenomena where the current is feeding into the fault is called the in-feed effect. So the impedance seen by the relay for a fault at D, for example, when I take this, so IA And if this current is ID here, here it's a ZBD plus ZF plus no, from here, if there is a relay looking here, right? This is what it should have seen the impedance of ZBD plus ZF. But in addition to that, it sees another current, which is the ratio of the remote feed-in to the local feed-in current, local current contribution, IA by ID plus ZF. So both the relays at A and relays at D, they don't see the actual impedance up to the fault point, but they see a much higher, a little higher impedance, that is higher impedance that is based on the ratio of the two currents that is fed into the fault here. So this same effect is there also on three-terminal applications. Sometimes a line is tapped and then provided it goes to another substation, and then this forms a three-terminal line. Now, when you look at it, if the fault uh, is within section A to T, then the relays will perform very well because the current flowing into the fault is same as what the relay sees. But if there is a fault at C, for example, the relay sees ZA plus IB by IA times ZC plus ZC. So instead of seeing just ZA plus ZC, it sees ZA plus ZC plus IB by IA times ZC. So it sees much higher current. So now, if you want to set the relay to cover all the faults, what we should do? We find out the shortest tap from ZA and then ZB and ZC, what is the shortest line section, actual line impedance from A to C and A to B. You take that and set 85% of that as zone 1 setting. The reason is, if I set 85% of ZAC, which is greater than ZAB setting impedance, then if C is open, then the relay might be overreaching that section. For example, let's take it is 1 ohm, 2 ohms, and then 1 ohm here. Then A to C is 2 ohms, and A to B is 3 ohms, right? So if I take A to B and set it to 85% of that, I'm setting it to 1.7 ohms, right? 1 plus 2 is 3. 85% of 3 is 2 plus something, right? Whereas this impedance A to C is only 2 ohms. So I will be overreaching on zone 1. So I have to take the smallest impedance, shorter of the two impedances from a local station to the remote stations, and set to 85% of that as zone 1. Zone 2 is 125% of the apparent impedance of the longest section, whatever we have. So ZA plus 1.2 C apparent. In this case, we have taken this. So the intent here is that I need to detect faults on this particular line section, and then whether I can trip instantaneously or with time delay depends on this apparent impedance. This has to be taken into account. Then another issue is the time coordination in distance relays. We have to make sure that the relay, that the relay operates only for faults in that section, and there are no unnecessary operations on the adjacent line sections. So now let's look at this. I've set zone A relay to 125% of the Z apparent, which we calculated based on the infeed. And then zone B to D is set to 85% for zone 1. When there is no infeed on the breaker, relay 2 reaches beyond D. For example, if this line section is set to 125% of 1.25, then it might reach, this is 3 ohms, 125% of 3 ohms is 3.75, and this was only a 0.5 mile line here. Then this setting here overreaches line D when if this breaker is open under contingency. The actual impedance up to this point is less than zone 2. Then I have a zone 1 and zone 2 relay too. So this overreaches zone 2. That means these two zone 2 relays, if they are set to the same timing, you will have a problem that if this will operate after a time delay of zone 2, but this relay also will operate with the same time delay of zone 2, which we assumed here previously for about 15 cycles. So after 15 cycles for a fault very close to D, both line sections BD and ABC, this line section also are open. That is not allowed. So what we have to do is we have to set the zone 2 time to another 10 cycles or 15 cycles so that you have coordination between this zone 2 and the remote end line zone 2. If this zone 2 overreaches the relay of zone 2 relay of the B2D. So just go through this and then try to understand these concepts. The key point you have to note here is we do not want any line section to trip if there is no fault within that line section. That is the key. And then it should not even operate for load conditions. That is also another point which you have to keep track of. Now, if the ratios of the current is too high, I said that if ZA plus ZC, and then we took this current as 1 plus the ratio of the two currents that is feeding the fault. If that IC by IA is 20, for example, then it is 21 times ZC. So the relay has to be set to a very large number. So your zone 1 setting is 85% of 2 ohms. The A to tap was 1 ohm and tap to C was 1 ohm. 85% of that. But zone 2, if you want to set that, you have to set 21 plus 1, 22 ohms, which is so high. One is 1.7 ohms is zone 1, and zone 2 is set to 21 ohms. It is so far, it might be reaching well beyond if that particular breaker is open at C. So what we do is we try to set it so that if the strongest end is always allowed to trip first, and it as soon as it trips, then if it becomes a normal two-ended line, a three-ended line, if one end is tripped, it becomes a two-ended line, and the relay operates after the breaker C opens. So this is also acceptable if we can allow the fault to stay for a longer time. If it is at stability critical line, or if we cannot allow this fault to linger on for a long time, we cannot use this. Similarly, zone 2, overreaching zone should consider apparent impedance, as I mentioned earlier. Zone 3 is 100% of the line plus 125% of the apparent impedance of the adjacent line. If it is not possible to set, then we have to go for sequential tripping. So this is the only option we have here. And we also look at some other factors that influence distance relay settings and operations. This is an introductory course where we just introduce you to the concepts of the relaying, and then you can build on it by reading papers or reading the books which are referenced here, and then you can look at it. One of the things that affect your zone 1 setting is the parallel line and effect of mutual impedance for ground distance elements. If the fault occurs at the end of the line with two lines in parallel, the impedance that the relay sees is less than the actual impedance of the line. So your zone 2 has to be pulled back. Similarly, if the fault occurs very close to that, the current is going through on the other line in opposite direction, the relay has a tendency to see less impedance than what it actually is up to the fault point. So your zone 1 relay cannot be set to 85% under such conditions. You may have to pull back the characteristics, pull back the reach to about 60% or 50% of the line. So these are important considerations, and fault programs allow you to do this and create different contingencies to see whether zone 1 overreaches and our zone 2 underreaches. The key point here is zone 1 should never operate for faults beyond the line section, and then zone 2 should never operate for faults, should always operate for faults within the line section. There is another situation where the current reversal takes place. There are two parallel lines. Fault is at the remote end. Currents are going away from the bus. But as soon as one of the breakers on the faulted line opens at the remote end, the current starts getting reversed on the healthy line. So when this current reversal takes place, the relay may operate if they have slow reset times on the distance elements. One is looking at as a forward fault in the initial condition. The healthy line at the remote end is seeing that as a reverse fault. But as soon as the breaker opens on the at the remote end on the faulted line, then the current changes directions. And that is also, we have to take care of that. Then another one is series compensated line. Essentially, you reduce the impedance of the line by, by putting capacitance in series with the inductance. So essentially, you are effectively reducing the impedance. When you do this, then your settings also get affected, and that is a special field, and we have to take care of that. Effective load on the lines. So yesterday, somebody asked what happens if if there is load. Load is taken as a positive sequence current, then you have to add that, and then it gets subtracted from the negative sequence for a face-to-face fault. Then you have to look at it, how that affects it. Okay. Then outer step conditions, when you have a fault in the system, there is a tendency all the generators speed up because you have a mechanical steam input into the turbines, and then the electrical output reduces because you're reducing the voltage at the terminal of the generator, and the current times the voltage is the power that is going out. So the mechanical energy that is fed into the generator is much greater than the electrical energy that is going out of the generator, especially if the fault is close by. Then the generators speed up because you're rotating it faster. The loading of the generator is the one which acts as a brake. Under balance conditions, they are at 60 hertz. And if you take away and create an unbalance, then they speed up. And then if you have a line that is taken out due to a fault, then you might create this unbalance on either side of this section if you have two regions. And then one might slow down and one might speed up. And then when this condition occurs, the whole system tries to readjust. So there will be current reversal, current exchange of power from one end to another end, which can, which changes the impedance that is seen by the relay nearly around 3 to 5 hertz per second. That is the rate at which the impedance changes. And the distance it might come in, distance seen by the relay, impedance seen by the relay might come into the trip characteristics, and the relay might operate. And we are not covering it. This becomes an advanced section. That is the reason why we left it. Here we take a setting example. We will go through this. Before this, let's take a 5 minutes break so that we will come back and regroup at around 2:20. It is 2:13 now. Let's regroup at 2:20 and go through this. Well, we will continue with this setting example. We have a line section A to B, that is what we are trying to protect. Then we have a line section BC, and then we also have a line section BD. A to B line is 15 miles long, B to C is only 8 miles, B to D is 25 miles. The positive sequence and zero sequence impedances of these lines are given as 11.25 for A to B, 6 ohms for B to C, and then 18.75 for B to D. And zero sequence are 39, 20.8, and 65 for these three lines. So this is what they have given us. And then the line angle is 75 degrees. Line impedance is 80 for positive sequence, and angle is 75 degrees for zero sequence impedance. So relay setting, CT ratio is given as 1000 to 5 at station A. PT ratio is 1000 to 1. So zone 1 is set to reach to 85%. That is the philosophy. Zone 2 is set to reach 125% of the actual impedance. Zone 3 is to cover 100% of the longest adjacent line. That is the apparent impedance. This philosophy has been predetermined for that particular transmission facility. So then we are supposed to set as per that. So zone 1 is 0.85 times ZAB times CTR by PTR. If we do that, CT ratio is 1000 to 5, it is 200. PT ratio is 1000. And actual ohms of the mile is 11.25. Positive sequence zone 1 is set to 1.91 ohms in the relay. And the relay angle is set to positive sequence line angle of 80 degrees. Zero sequence compensation factor, K0, that is Z0 minus Z1 by 3Z1. You go and then calculate that. It turns out that this K0 is 0.824 at minus 7 degrees, right? And zone 2, we say that it is supposed to be set to 125% of the actual impedance of the line. So you just go through the same calculations and you set zone 2 to 2.81 ohms. Most of the relays will have common settings for angle of and K0 settings. Separate K0 setting is also possible as an option on certain relays. So you have to make sure if you want to set it, because line section AB may have some other K0 setting. So when if you look at 25% of the adjacent line section, you can set this K0 to some other value. Does this reach overreach zone 1 setting on? Check whether this reach overreaches zone 1 reach settings on remote end. What we are talking is, if I set zone 2 from here to 125% of this line, which is 25 miles, you don't want this to overreach adjacent line section. Actual impedances, what are set on that. Of course, you have an in feed here from here. The actual impedance looks like the fault looks like it is farther than the fault what happens here, but we assume a contingency that this is not in service, so it becomes radial for coordination purposes. In our example, the answer is no. Zone 2 relays are time delayed to coordinate with 15 seconds. So if let's look at it from the distance, this was set to 85 miles by 85% of 15 miles. Right, from the approximately it is set up to 15 times 0.85 as zone 1, 12.75 miles. And then we are assuming the same impedance here. So let us see what is BC zone 1 set to 85%, right? 0.85 times 8 miles, it's 6.8. And then this is 15 miles. So the total mileage will be 6 plus 15 is 21.8 miles. So now I take 15 miles and multiply it by 1.25. It is set to 18.75 miles. So it is not overreaching the zone 2 of this. I just use the miles because the impedance is the same for all of them, and I could do that. Otherwise, normally you have to take the actual impedance value and then try to calculate that. Okay. Zone 2 relay is time delayed. Is there any question? No. Zone 2 relays are time delay to coordinate with remote and breaker failure time, typical 15 to 30 cycles. We went through this, right? If zone 2 overreaches remote zone 1 and zone 1 relays coordinate with zone 2 time. You have to do that, like we talked about it. Forward reaching zone 3. We know the apparent adjacent longest line section is BD, is 1.25 and 1 plus 10 power 3 by 10 power 3. That is, we are assuming the same current coming in from 2, and it is 46.875. And then 11.25 plus 46, and then you are converting it to secondary ohms. So that comes down to 11.625. Zone 2 overreaches bus D, but if the line section is out of service, so zone 3 actually here, it is not zone 2. So time delay is set much longer. Zone 2 time delay plus breaker typically 40 to 45 cycles. We should say, where is that? Yeah, this is zone 3. So the time delay is set to about 40 to 45 cycles. Okay. Then distance ground scans, if you look at this, you are setting it to zone 1, zone 2, zone 3, and BC zone 1 and zone 2. Similarly, you have a BD. You have to make sure that it is also coordinated with that. And B, from B to looking towards A, you have 85% zone 1 and 125% zone 2. Ground overcurrent schemes, phase distance and ground overcurrent schemes were used. As I mentioned earlier, there are you need 6 different calculations to detect all types of faults, 3 for phase to phase and 3 for phase to ground, as I mentioned. So if in the electromechanical world we had to put, these are all single phase, measuring elements, I should have put 6 boxes for this, for zone 1. And then you need 6 more boxes for zone 2 to provide protection for the last 15% of the line section, because zone 1 is set to 80 to 85%. So instead of that, they came up with a very brilliant technology. Any fault involving ground will have a current through the ground neutral, right? So you can use a ground overcurrent element to detect faults of the ground. And they used what is called polyphase distance element, one box that can detect all types of phase-to-phase faults, and double line to ground and three-phase faults. So they use 2 boxes instead of using 6 boxes. And then for 2 zone protection, they needed another distance element. So they used 3 boxes, because ground directional overcurrent with the time overcurrent relay can provide protection for zone 2 also. So this is how the Westinghouse came up and used, and that saved money for people. Now it is irrelevant because you have a microprocessor relay which has so many elements, and you can use any one of these. So distance relays are time coordinated based on the reach, as we discussed. The ground overcurrent relays also are coordinated with time. So if there is a fault in adjacent BC, that has to operate faster than the ground overcurrent relay from A to B. Okay, so that time coordination was typically like zone 2 time of 15 cycles. They were also given the same time for coordination purposes. Now let's look at the fault clearing times on the transmission line, right? So if you look at it, zone 1 is set to 85% from both ends, and zone 2 is set to go beyond to cover the last 15 sections, end sections from 15 to 85 to 100, or 0 to 15, right? So all faults within this 15% to 85% of the lines are cleared by faults without any time delay, because zone 1 relay operates at both ends, and they open the breakers without any intentional time delay. Now, if there is a fault in this section, remote 15 to 85% to 100%, then this zone 1 relay operates and trips it, but the fault is not cleared because here zone 2 relay is timing out, and after 15 cycles, it trips. So the system will still have a fault which is lingering on till zone 2 time delay. So for end zone faults, either closing faults or remote end, last 15% of the remote end faults, the faults are cleared after zone 2 time delay expires at both ends. Right? So now the question is it okay for us to delay this tripping? This may not be possible where you have, let's go back here. So if it is a stability critical line, that means you might lose some of the generators, or they might fall out of step. We have to trip as soon as possible. We cannot allow this delayed tripping for faults either here or in the first 15% or the last 15% of the line section. For this, we have to use some kind of communication between two ends to know whether the fault was on the line or not. And these are called communication assisted schemes. But other schemes which we have already talked about are pilot schemes. Pilot schemes are phase comparison, current differential, and then directional comparison schemes. We use this. Here, we already talked about current differential and phase comparison because it exchanges information of the CT, current information at both ends, and then makes a determination to trip for 100% of the fault. So it doesn't have a zone 2 backup as we talk in the distance elements, but it is a unit protection. So it operates without a time delay for faults within that line section. The third one is called directional comparison schemes using distance or directional overcurrent relays. We have not talked about it. So we will look at it how these are done. The communication medium that is used here is either power line carrier or leased telephone line or microwave or fiber optic cable. So these are the four ways of exchanging information from one end to another end. So in the case of current differential schemes, we were exchanging the current information, right? Actual current flow information from one end to another end. Phase comparison was looking at the phase relationship between the currents. And in the pilot wire, in the directional comparison schemes, we are not exchanging any currents or voltages from one end to another between the ends. We just make use of a decision made by the zone 1 and zone 2 relays or the reverse looking relays and make a determination whether the fault was on the line or outside the line section. So they use directional relays to determine fault position relative to the protected line and communicates that information to the remote end. The information is used to achieve faster tripping at both ends. So we will use some terminologies in the pictures, in the next few pictures. So we will try to look through that. Underreaching, as we mentioned, is always zone 1, which is set to reach not to 100%, but to 85%. Overreaching is a relay, which is zone 2, which is set to go beyond the line. It is normally set to 125% of the line section. And then various tripping schemes are originally designed with electromechanical relays and had distinctive names. So, the schemes which we discuss now, they were all based on the number of relays that they had to use in electromechanical world, because each box had only one function, right? I had one zone 1 phase and zone 1 ground, zone 2 phase and zone 2 ground, or zone 1 KD relay, which detected all phase faults, and then they have a ground overcurrent relay that provided zone 1 and zone 2. So you had two KD boxes, two electromechanical relays, one for zone 1, one for zone 2 to detect all phase-to-phase and then double line faults, 3-phase faults, double line to ground and 3-phase faults, and one ground overcurrent element that provided with that inverse time overcurrent relay that gave zone 1 and zone 2 coverage for ground faults. Microprocessor relays combined various schemes with the same nomenclature. So what they call as one scheme now in a microprocessor relay may not be the actual representation of how they used to do in the in the electromechanical world, but they have used the same terminology, but added a few more features in the existing one. So we will use zone 1 for zone underreaching and zone 2 for zone overreaching. And let's look at the very first scheme here. Uh, so when you look at this here, I have zone 1 relay and set to reach up to 85%. And zone 2 is also there, but that is with a time delay of 15 cycles, right? Similarly, I have a relay zone 1 looking from B and towards A, and zone 2, which is set to go uh, beyond line section A for 25% more with a time delay of 15 cycles. Now, we are covering, first is called direct underreaching transfer trip schemes, DUTT. So now what it is if the zone 1 relay operates at line A, I know for sure the fault is on the line because I've already made the decision here telling that the fault is within the 80 to 85% of the line section, right? So as soon as this detects a fault, what I do is I send a command to directly trip this breaker at the remote end. So I know I use a communication channel to send a trip command for both the local breaker as well as the remote breaker. Similarly, if this relay operates here, I send a signal to open this breaker also along with this breaker. So we are exchanging the trip signal, the open command to the breaker to be sent to both the breakers at the same time. This is called direct underreaching transfer trip. The underreaching DUTT comes because we are using an underreaching zone 1 relay to transmit this to the remote end. Okay. So now you look here, I have zone 1 relay, which is coming in to trip the breaker. And then as soon as I receive a signal from the remote end, that comes also that trips the breaker. When you look at this receiver, what is transmitted from the remote end is their zone 1 relay. So if both zone 1 relays operate, they exchange information to trip the remote end breakers. The problem here is you have to make sure that your communication channel is very secure. If you get a noise, what happens here? You just trip the breaker. Suppose if this receives a noise from the other end, and then it will unnecessarily trip this breaker. So the security of this scheme is highly dependent on the channel, what we use. So sometimes dual channels are used to provide security for this. Then they said the schemes they used and the channels at the time, they were not very secure. So what they did was they said, okay, we should have another local determination to make sure that the fault is on that line when we receive a signal from the other end. So now I have zone 1 relay operating and tripping the local breaker. But when a fault occurs on the line, what relays pick up? Zone 2 also picks up, right? And the zone 2 picks up, but it trips after 15 cycle delay. So if zone 2 has picked up, and if I receive a signal from the remote end, which is keyed by the underreaching element, then I know the fault is on the line. So they make use of the determination of the fault with zone 2 also that says that the fault is in this last 15% of the section, and we bypass the timer and trip. Suppose if we don't receive this, what happens for a fault here? The relay trips after 15 cycles time delay. So essentially, if with this scheme, with the direct underreach transfer trip or permissive underreach transfer trip, faults from 0 to 100% are cleared without any time delay. The only time delay that we are looking at is the channel transmission time, signal transmission time from one end to the other end. We don't have to wait for 15 cycles zone 2 time, but it is reduced drastically depending on the channel, what we are using for communication. So permissive underreach, it's like I said, zone 2 element picks up, and then we get a signal from the remote end that is triggered by zone 1, and then it trips right away without any time delay. Zone 1 trips the breaker and keys the transmitter, and it receives a signal here. If zone 2 has already picked up, we know the fault is in front of the relay, and then it trips right away. And similarly, if the fault is outside, what happens here? The zone 2 operates here, but we don't get a signal because zone 1 never picked up for a fault because the fault is behind the relay. So we don't get any operation here. And this trips after the time delay. Okay. Then permissive overreach transfer trip scheme. So in the direct underreach transfer scheme and the permissive underreach transfer trip scheme, what was the element that was keying the transmitter? That was the underreaching element. Zone 1 element was keying the transmitter. So as the name permits here, it's zone POTT scheme. It just takes zone 2 relay to operate. So when you look at permissive underreach transfer trip scheme, we needed two elements, zone 1 and zone 2 relays here in the electromechanical world. So when you look at overreaching scheme, they eliminated zone 1 relay completely. So what they do is they had only one relay looking farther than beyond the line section from both ends. If both of them tripped, both of them detected a fault, they exchanged information and tripped both the breakers. See, let us see if it makes sense for you. Suppose if there is a fault on the line section here, either in last 50, anywhere in this section, both the zone 2 relays will operate, right? As soon as zone 2 picks up, it at remote end, it keys the transmitter there at the remote end. As soon as the zone 2 picks up at the local end, it keys the transmitter. This information goes to the remote end receiver, and zone 2 has already picked up. As soon as it receives, it trips without a zone 2 time delay that we have set to for 15 cycles. Similarly, at the local end, zone 2 had picked up. It received a signal from the remote end telling that the fault was in front of the relay, and it trips without any breakers. Suppose in the leg, what happens if one side, one of the breakers is open here? Suppose the remote end breaker is open. If the fault occurs very close, right outside the breaker, very close on the line side of the breaker here, zone 2 element picks up, but it is waiting for the time delay because it doesn't receive any signal because the relay does not operate at remote end because the breaker is open. So what they did was, when the breaker was open, one scheme used an auxiliary contact of the breaker to permanently key this transmitter to the remote end. If the breaker is open breaker transfer keying was used to just send a signal here as soon as this impedance element picked up, and because it has gotten a permanent receive from the remote end, it tripped without any time delay for end zone faults. The modern relays now, they don't make use of the breaker. They used what is called the echo logic. They use another element inside, which is looking in the backward direction. So if the fault is behind the relay, what does it do? It sends a blocking signal to the remote end. So if the reverse element has not picked up, and if it receives a receiver, if it receives a logic from the remote end, it sends and then keys the signal to the transmitter end. Suppose I said that if this breaker is open, for example, in this thing, if there is no fault in the reverse direction, and if there is a fault in front of the relay, here zone 2 picked up and then sent a signal to this end. And then we know that the reverse element has not picked up. And then what it does is it right away trips this breaker here. And then it echoes the logic to send it back to the remote end. So echo logic is also used for high-speed tripping, I should rephrase all the things I said. Suppose if this breaker is also closed and if the source is open at this end, and if the fault occurs here, there is no current contribution from this end, this breaker is still closed, and then we have a fault very close to this breaker, this zone 2 picks up and impedance elements and sends a signal here. Because no element has picked up at this end, what it does, it sends a logic to the remote end to key it sends a signal to the transmitter to key the signal back here to bypass this timer. Go through the logic, and then you will. It's not that difficult to figure it out. Could be zone 3 or zone 4, depending on reverse-looking zones. Various manufacturers use various terminologies for this. SCL use zone 3 for reverse-looking element, and then whereas GE uses zone 4 for the reverse-looking element. And it could be different for other manufacturers. Please make sure that the embedded logic uses which zone, and you appropriately set the zone as zone 3 and zone 4. Weak feed trip. Suppose if there is no voltage current coming in here, if a fault occurs here, what happens to the voltage? The voltage dips because there is no current up to the fault point. Voltage at the relay location will be same at the relay location here. This is the relay location. The voltage at the relay location and voltage at the fault point will be pretty close. If there is no current flowing in, there is no voltage drop across the line, and it will be 0, right? So if this relay picks up, the remote end relay picks up and sends a signal telling that there is a fault on the line, and because there is no current for this relay to operate, then it looks at it. If the under voltage relay is used, if the voltage is below a set value, and then if it receives a signal, and then it also checks whether there is a fault behind. If there is no reverse fault, then it trips the breaker here too. It isolates this breaker. Whether this breaker is closed or not under this condition, because if the current source is so weak, it may not operate. You just isolate the faulted line section without any time delay. Hybrid part scheme, they called it. The GE called the scheme with the ecologic as hybrid part with the reverse-looking elements, and that was GE's terminology. But Schweitzer Relay calls it as POTT. Like I mentioned earlier, these names all came, are all the names which they used with electromechanical relays, but the same names are used even in microprocessor, but they have a lot more logic into that, added into that. So when in electromechanical legacy time, when you say part scheme, it was a Westinghouse scheme, and if you say hybrid scheme, it was a GE scheme. But both of them are POTT schemes, and Schweitzer calls it just a part scheme. There is another permissive scheme, but it's called directional comparison unblocking scheme. The name is uses unblocking, so it causes confusion. This was a scheme that was developed by Westinghouse protection group, and this is also a permissive scheme. And they're using frequency shift carrier communication. That is, you have a normal carrier frequency which is exchanged between the transmitter and receiver at both ends. And then as soon as a fault occurs, the frequency is shifted, then you send a trip frequency on that. So you know that you are getting a trip signal from the remote end, right? What happens here is, this is not here. If the signal is lost, if there is some problem with the signal, what they do is they momentarily give permission for the relays to operate for 150 milliseconds if the signal is lost during the fault. So essentially what it does is, if there is a fault and at that time suddenly you find that you are not getting any communication signal from the remote end, if zone 2 had picked up at the local end and then the communication equipment says that I lost the signal, it still allows it to trip for 150 milliseconds. Suppose if the signal was lost before the fault, after 150 milliseconds, this scheme is disabled and it works like a stepped distance scheme. So the difference between DCUB, directional comparison unblocking scheme, and then a POTT scheme is that if there is any loss of signal during 150 milliseconds, as soon as when a fault occurs, it overtrips. So this was used because a communication signal is sent only on one phase of that using a communication equipment in most of the cases. And if there is a fault very close or on the top of this PT where it is transmitted, you might lose a signal. So this was allowing the remote end to trip faster for local faults. So this is how we show that as a pulse signal, which is 150 milliseconds. So if you lose the signal in the signal that is monitored here, then it just provides a momentary 150 milliseconds pulse to this. And if zone 2 has operated, it trips the breaker without any time delay. Now, there is another philosophy when you look at all these schemes, what we talked about, DCUB or permissive overreaching schemes, permissive schemes, the transmission of the signal was taking place from station A to station B when there was a fault on the line section. So we were exchanging information of the distance elements operating for the fault, which was looking towards the line section. So we are trying to transmit a signal on the line which is already faulted. So they came up with another scheme which we said, how do we know that it is going to reach the remote end? If it doesn't reach the remote end, there'll be delayed clearing, right? So they came up with another scheme called directional blocking scheme. There is a question, let us see what it is. Yeah, the question they were asking is, that is asked is, do we have uninterrupted or power supplies to energize the communication devices? No, we have a battery at a substation, right? That is the DC, and that has a charger, and then that is supposed to be maintained. And that is the one which is giving the DC. So most of the times, that is not that is just like an uninterrupted power supply. The DC is always on. In case if you lose a carrier device communication, you do lose communication, then you will get delayed tripping in other cases. But most of the times it is a DC inside, and we don't have an UPS inside a substation. On loss of AC charger to the batteries are designed to last for 8 hours at least, or 8 to 12 hours, depending on the philosophy of the of that substation owner, which they can either put a second set of batteries as redundant batteries. At least one half of it will be working because the load is less, so it might stay for a longer time, or they are oversized so that it can stay without charging for more than 8 hours. So now in this directional comparison blocking scheme, we are trying. There is one more question. Let us see what it is. Yeah, it's the same. Okay. Then when you look at the comparison scheme, we use another element, reverse-looking relays, to key the transmitter. When I mentioned that if it is a direct underreach transfer trip or if it is a permissive underreach transfer trip, zone 1 is keying the transmitter. If it is permissive overreach transfer trip scheme, directional comparison unblocking, which is also nothing but a permissive overreaching scheme with a provision to provide faster clearing on loss of communication signal when a fault occurs. They are all permissive schemes, even though the name says directional comparison unblocking scheme. Now, directional comparison blocking schemes use relays to look behind from each station. So at station A and B, we are protecting from a line from A to B. There is a distance relay which is looking behind from A and for the section behind it. And there is also a relay at station B which is looking beyond that section, looking backwards. And then what it does is it relays pick up at both ends for faults on the line. And then because it's a fault on the line, reverse looking elements do not operate. So these relays pick up and wait for a signal from the remote end. If it doesn't come within a set time delay, which is 1 or 2 cycles, then it trips the breaker. And so if the blocking signal is received within this time, then it delays the protection, telling that it is zone 2. It is easier to look at this in a picture. I have a reverse looking element looking behind, and then here looking behind too. Sometimes they use directional overcurrent elements looking in backward direction like this. So now if there is a fault on the line, for example, then what elements operate? Here, zone 1 is always there, so zone 1 trips for that. Suppose if there's a fault in the end zone fault here the local element trips and the remote element is waiting for a signal. Because the reverse elements are keying the transmitter, the local here, we never receive a signal for that. So zone 2 is waiting for 1 or 2 cycles. Because it did not receive any signal from the remote end, it trips for a fault within 2 cycles after, after waiting for a blocking signal. Now, if there is a fault behind on this line here, if there is a fault behind, what happens? Zone 2 element here picked up at station A, and then it is waiting here. And then here, the reverse looking element also operated. As soon as the reverse looking element operated, it sends a signal here, and this is 1, but that is negated here. So then it blocks the tripping from zone 2, and it doesn't bypass the zone 2 timer here. So what will clear this fault? After the zone 2, the local breaker should have operated. If it doesn't operate, the zone 2 relay operates after 15 cycles. So the advantage of this scheme is that you are never transmitting any signal on the power line carrier, if they're using power line carrier, to the remote end on a faulted line. And the second thing is, if I don't get the signal, what do? I trip it faster and then don't wait for 15 cycles. There is a catch for this too. If there is a problem with this communication device, then you will have bonus trips. For a fault in the adjacent line section, this line also will trip. So this is getting a lot of attention here now with many the supervisory entities on all these lines to make sure that it trips only for faults and not for anything else. And these are getting looked into because there are what are called carrier holes where we might lose a signal for a fault. And most of them are trying to go for permissive schemes. But this is still used widely in the electric utility in the United States. So essentially, I think that is all we have, right? So what we covered today on was after the break was transmission line protection. And then we went through the concepts of transmission line distance protection. We already looked at current differential schemes where they exchange information of the current. Then we now looked at volts, the ratio of calculating the impedance up to the fault point by dividing the voltage by the current. And then we found out that we need to use faulted voltage as the voltage input, and then the currents are depending on the type of the fault. For A to ground, I cannot just add the phase current. I have to add a portion of the current flowing in the neutral. So I have to use IA plus K0 times IN. And then if I divide voltage by that, then I can measure the impedance up to the fault point. Suppose if it was a phase-to-phase fault, we found that we have to use the phase faulted phase voltage VAB for A to B fault, and divided by the difference in currents on the two phases, IA minus IB, to get the same impedance as a positive sequence impedance up to the fault point. So we went through that, and then we also looked at how the relays are designed. In digital relay, static relays, they used phase comparators to look at the phase relationship between V and V minus IZ. IZ is actually the voltage that is developed across the setting that you put inside the relay. And then if these two are in phase, we block it. And if they are on 180 degrees out of phase, we allow it to trip. And to develop the characteristics in the digital relays, they used phase comparators, whereas in the microprocessor-based relays, they use products. You can look at the equations. And they also use the directional elements, negative sequence directional elements. That looks at the phase relationship between voltage, negative sequence voltage, and negative sequence current, or zero sequence voltage and zero sequence current, or to make directional decisions. That is used widely. And then we also went through setting calculations of a simple radial system and looked at it, and it introduced the concepts of apparent impedance, where the relay, when it calculates, it sees higher impedance than the actual impedance up to the fault point due to currents being fed from some other lines at the remote end. That is called the in-feed effect. Then we also said that for faults beyond zone 1, which is set to only 80 to 85% because of the inaccuracies of parameters of the line, or instrument errors, or design errors, we just wanted to confirm that it is on the line, the fault is on the line. We set relays with no intentional time delay up to 80 to 85% of the line section. And to cover the remaining line sections, we use zone 2, which also provides a backup for faults on the adjacent lines. And they are typically delayed about 10 to 15 cycles, I said. But essentially, that setting has to be greater than the breaker failure time and the relay operating time and breaker operating time at the remote ends. And we went through that. Then if it is a stability critical line where we are supposed to clear faults without any time delay, then we have to make use of communication assisted schemes, or we have to use relays that trip excuse me, that trip for without any delay for faults on at any location on the line. What are those relays? We can use current differential schemes where they exchange information of current from one end to another end. And then we talked about the alpha plane, and they are using fiber optics. These relays are widely used, are becoming more popular now because of availability of fiber for transmitting information from point A to point B. And then if you are using distance schemes, we make use of any of the communication media, power line carrier, or fiber optics, or microwave, and then we send the element operation information from one end to another end, and decide whether to trip or to wait for some time based on the scheme we are using. So we covered 4 schemes: direct underreach transfer trip, where we know that zone 1 relay operates always for faults on the line, and we directly send a signal to trip the remote end. And then zone 2 is permissive underreach transfer trip, because we don't want any false signals to come and trip unnecessarily. So we try to make sure that there was a fault on the line by monitoring the signal received from the remote end with the zone 2. And then we also looked at directional comparison unblocking schemes, like if the signal is lost during when a fault occurs, we momentarily allow the relay to operate for 150 milliseconds or 250 milliseconds, depending on what has been set in either in the communication equipment or inside the relay. Also, you can do that. And then the 4th scheme was not to transmit any information on the signal on the line when a fault occurs on the line. That is called directional comparison blocking schemes. We just, as soon as it detects a fault, we wait to see if we can get a block signal from the remote end. If we don't hear from anything from the remote end, we trip right away. So these are different schemes. As I mentioned, all these names came from the legacy systems applications and where power line carrier was used most of the times. And then, now you have fiber, you have other communications media available, and then microprocessor relays. It doesn't matter. You can combine a lot of them. For example, if there is a 3-terminal line with a weak source, and if you want to use a permissive scheme, then it may not operate at all for faults on the line because the current coming from there is extremely weak. So under such conditions, you can combine the blocking and permissive scheme, and then you can mix and match all these schemes according to what is required to make sure that you are tripping the line without any time delay. So that is all for today. We will stop here. I've gone up to 3 o'clock. We will talk tomorrow. We'll pick up with breaker failure and auto sectionalizing scheme, restoration schemes that is used in the power systems network. And then we will go into rotating machines and then briefly touch on schemes that are used for rotating machines. So if you have any questions, you please send on a chat this thing, then we will try to look at it. Or if you have any questions in the morning, please do type in and we will answer that before we take up the next session. And then we will also cover shunt reactive compensation equipment protection, that is shunt reactors and then shunt capacitors. Thank you. Have a nice evening, and we will again resume tomorrow morning.